Hi there, I'm Renee Jones, and welcome back to Research Snapshots with ICIDS. In this series, we'll be meeting researchers at the cutting edge of climate change, energy transition, and disaster risk research at the Australian National University. Today, we meet Dr. Felipe Torres and Shuqi Xu, who are conducting world-leading research in the exciting field of thermodiffusive desalination. We asked Dr. Torres what drove him to conduct this research.
We feel that we're heading towards disaster. There's a couple of red flags that we're seeing already, which is massive population growth, and the climate change has become worse and worse, the impacts of climate change. Some of the impacts of climate change are periods of drought, and those periods of drought essentially affect large amounts of crops. So you have a bigger demand for food, but a fewer supply of food because of the potential lack of water. So I think food security and water security are the big issues of our time. And one way of solving this would be to get access to an unlimited source of fresh water. And the limited source of fresh water that we see is coming from the ocean. So water from the ocean has salt. If we find methods of removing the salt, essentially cheap methods and things that are accessible, we would be able to unlock an unlimited amount of fresh water from the ocean.
There's a lot of water on our planet, but most of it is too salty to use. Removing the salt or desalination isn't a new idea, and there are many large desalination plants worldwide. We asked Dr. Torres how the existing systems work and what's the problem with them.
The way we currently do it is by a method that's called reverse osmosis. We desalinate more than 80 million cubic meters of water per day with reverse osmosis, more than 100 million cubic meters of water a day, a lot. But still, this is much less than 5% or 4% of the needs that the humanity needs. So reverse osmosis has not been able to increase more because it's a very energy-intensive process, and it has a lot of issues like materials degradation. It has fouling and scaling. And it's something that actually impedes a lot the uptake of this technology beyond countries that can afford such an expensive method. So we have proposed a method called thermodiffusive desalination. That is the world's first thermal desalination method in which water is kept in a liquid phase there's no evaporation and there's no freezing. Thermal desalination methods have been around for thousands of years, but all those methods used condensation, evaporation, and subsequent condensation. But our method is much simpler than that, and I think that's the beauty of thermodiffusive desalination. It's a simple method in which we have a single channel, we apply a temperature difference through the channel, and we flow water through it, and we're able to separate the species. So this is a very simple device where we have two copper blocks, one on the top and one at the bottom, that will form a cavity for a water bath circulation, and also they're going to form the top and bottom walls of our 1 millimeter high channel. So we circulate at the top. This is the direction of the water circulation. We preheat water, and we flow it through here through this cavity, and it goes out through here, and it's circulating at a prescribed temperature. And then the cold side does the same thing. So the saline water goes through here. It takes maybe a minute or so to reach the other side. Once it reaches here, we split it into two, and then we get the high salinity and low salinity. But then once you get that, we measure the salinity difference between low concentration and high concentration. And then we recirculate if needed, if we want to drop the salinity further. So it's a very simple device.
Working alongside Dr. Torres on this project is PhD scholar Shuqi Xu. We asked Shuqi about the challenges they faced on the project.
Initially, at the very beginning, we designed this device. We're saying that this is a single concept. Look, we just got hot, cold water, and a saline water flow down. We're going to get desalinated water, and the truth is that we got nothing. There's no concentration difference at the end. We got absolutely nothing, and we started wondering why. And then COVID came, and I had to be forced to do some at-home work. That's when I started doing CFD modeling, like computational fluid dynamics modeling, and then we realized that basically, the thermal diffusion is a very slow process that we need to control, like the flow speed, very nicely through the channel. So there's a paradox between the yield, which is how fast we can desalinate, and the energy, like how much heat flux is going through this. So we're trying to strike a balance between those two.
Water security is emerging as one of the biggest challenges we are facing worldwide. We asked Dr. Torres if this new technology is intended for use of drinking water or other uses.
Honestly, I think it's going to be very hard to use it for potable water. And the reason is that the phenomenon gets weaker and weaker as the salinity drops. Our main target right now, let's say market-wise, our main market would be agriculture. And agriculture is responsible for more than 70% of the worldwide freshwater use. So in agriculture, what they usually do is that they try really hard to find the freshwater resource, or underground, or they make wells. And that's something that is going to run out at a point, because even the underground water is getting polluted, and it's getting more scarce. Being able to produce a method that is more accessible for desalination that could be used for agriculture could change the way we do things, really, and could be a major advancement towards food security and water security worldwide. Yeah.
Fascinating research that offers practical, world-changing possibilities. Thank you, Dr. Torres and Shuqi, and thank you for watching. You can find more information in the links below.